Is the participants list popping up on your view of my share screen? Or
No,
just the slide?
no, it's only the slide.
Okay, good. I just want to make sure nothing's in the way.
Oh yeah, since Ping is in Massachusetts, they may have been affected by the storm. Yeah, so in case he is unable to join, Andrew or Mohan, would you like to chair the next session? I'm going to make Andrew. Mohan is not there, I guess.
Okay, I can do that.
Thank you, Andrew. I have made you co-host as well. And we will start in a few minutes. So I just want everybody to take a look at the chat box where it's at the bottom of your Zoom screen. And I have posted the link for the call for papers for CODASPI 2021 because the deadline for abstracts is just a month away, September 3. So, I thought I would share this with all of you. You may be interested in submitting a paper there. So Barbara Carminati of University of Insabria in Italy and I from University of Houston are the co-chairs for CODASPI 2021. And, please consider CODASPI seriously for your best papers.
Okay, I'm switching to my computer. Can you let me in?
Yes, I did let you in just now.
Okay, great.
Yeah.
And how many papers in this session?
Right. So there is one tutorial and okay, let me also give you the oh, okay, Ping is here actually. Yeah. So we can continue with you, Andrew, or we can go with Ping, because Ping, I was worried that you are in Massachusetts and there was a storm there.
Oh, yeah, it was okay, not that bad.
Oh, okay.
All right. I'm relieved.
Thank you. Yeah, we were thinking you may not be able to join, so Andrew had kindly volunteered to be the session chair in case you are not able to join.
Oh, okay. Yeah, it's okay. It's just I have so many meetings these days for some reason.
Okay.
Way more than before.
Yeah, everything has to be done virtually, right? So
yeah.
okay, so with that, Ping, I think you can take over. We have a couple of minutes, so I was telling all the participants to take a look at the chat box and where I've posted the link for CODASPI 2021 call for papers.
Mm-hmm.
Yeah. So with that, I'm going to mute myself, and then you can start.
Okay, so we still have like a few minutes.
Yeah, you can start in a couple of minutes. There's no rush.
Okay.
Yeah, we have a break at 1:55. So we have a tutorial, then a long presentation, then a break, and then 2 long presentations and a short presentation at the end.
Okay.
So yeah, and also I've asked Andrew and Mohan to make a short presentation at the end of the session about the plans for IWSPA 2021.
Okay.
Yeah. So we'll end on that note.
Rakesh, when I click this chat box, it's empty.
Oh, that's interesting, because I guess you just joined on the computer, right?
Yeah.
So you lost that. So let me just send it again. Okay. Yeah. Every time you open a new Zoom session, it gives you an empty chat box. It doesn't give you the history. So
I see.
yeah, I'll post it here. So here's the link.
Oh, great. Yeah, got it. Thank you.
Yeah, sure. Yeah, it doesn't give you the history. That's what I found out, because I was attending CODASPI conference, last 2 days, and I created a new Zoom session. I also got an empty chat box. So, okay. So I'm going to mute myself now. So Ping, you are the host now.
Oh, okay. So we'll start at in 2 minutes. How about that? 2 o'clock exactly.
Yeah, 2 o'clock Eastern, 1 p.m. Central. So
yeah, 1 more minute. Okay, so let's get started. I hope everybody enjoyed this morning's session, and now we are in session 2, in the afternoon session. My name is Ping Chen, and I'm from UMass Boston, and I'll be session chair for this session. So I want to welcome everyone to join us. This afternoon session, we have one tutorial from Daniel Lee and Rakesh Verma. And then we have 3 long presentations, and each will be 15 minutes plus 5 minutes for question and answering. And also one short presentation that will be 2 minutes and plus 5 minutes for question and answer. So let's get started with the tutorial from Daniel and Rakesh. And who will be presenting? Is Daniel or Rakesh?
I will be Daniel. So should I get started?
Yeah, go ahead. Let's start it. Yeah.
All right. Well, first I want to thank ISPA for inviting me and Dr. Verma to this tutorial. It will be on adversarial examples and how they are being researched in the text domain. I am a PhD student in the REDOS lab at University of Houston. So before we begin, I just want to give a brief outline of what we'll be covering. We'll be talking about the adversarial machine learning environment, give some background and notations that we'll be using throughout the tutorial. And then we'll be introducing some continuous attacks that have been used, talk about why it's hard in the text domain, look at some approaches that are being done just in NLP tasks in the deep learning for text. And then we'll look at some adversarial text research that has been going on, look at some defensive approaches, and then we'll conclude with some question answering. So before we actually get into adversarial examples, I did want to acknowledge that the study of adversarial machine learning was growing first way back in 2004. And also later 2005, a group with Dalvey and also later with Loud and Meek put a great focus on the fact that machine learning, that yes, it does well, but you have to also take into consideration the adversary, meaning that it is not a benign environment, especially security-wise, and there are adversaries out there that wish to attack your model. And Loud and Meek gave a very simple approach to attack at the time what was a very popular spam filter called spam base. And they essentially did a good word attack where they collected words that only appeared in emails that were classified as legitimate, and then just inserted those words into the phishing emails that they want to bypass the classifier, and they were able to do that quite successfully. So it kind of highlighted the fact that we have to take into consideration the adversary in a machine learning problem. Later, we also had another work from the group at Berkeley, authored by Burino in 2010, that took a more systematic, I guess, approach and look at the idea of security machine learning. And the group approached it with 3 dimensions. One is the attack's influence. So causative being, are they trying to make a attack on the training data or during the train time, or exploratory where we have a finished model and they want to attack it after it's finished. And adversarial examples is actually falls into that domain of exploratory or test time attacks. They also want to look at the way they want to compromise the system, the violation. Are they trying to raise false negatives wherein they are avoiding the detection or avoiding the model's ability, or they're trying to attack the availability in terms of raising a lot of false alarms so that the user of these advanced systems begins to ignore them or even ultimately may even turn them off. And then specificity. In specificity of the attack, we're talking about as the attacker, do I want it to specifically go to a certain target, or does it not matter? I just want to completely make the classifier just choose anything else but the true target. And of course, in a binary setting where you only have 2 labels, both targeted and indiscriminate are essentially the same thing. He also looks at kind of the security goals that we have in mind when we're thinking of machine learning, and also looks at the threat model. And the threat model He's looking at things as what is the goal of the attacker, in other words, or what kind of violation they want to do, or those three dimensions of that attack. And then the capabilities, how much do they have access to perform their attack. Several years later, this seminal work in adversary examples was published, and it was published in a preprint, and I think later it was published as a poster in another well-known conference. But in this work, coinciding with this work, deep learning had gained a lot of popularity in the community of computer vision. And as a result, this also drew a lot of attention when they discovered this idea of adversarial examples. And adversaries are basically what you see in this illustration. This comes from a different paper, but it very well illustrates what an adversarial example is. And it's kind of the picture that if you're doing any kind of talk on adversarial examples, you kind of have to include that picture. So this is the original picture here. And we can clearly see as humans that this is a picture of a panda. And we see that the model is also depicting as a panda. And then an adversarial example is you do some kind of a modification to that image here. We're adding different pixel values. And then we see the final new image. And as humans, we cannot see these small changes. But you can see that the classifier is now misclassifying it. And in fact, it's even more confident now that it's a given, which is a type of monkey. And so adversarial examples, there are two kind of facets. It needs to be, to the human, somewhat imperceivable in terms of the change, but to the model, it produces a high impact, a high change. And we can kind of dramatize this idea if we take the idea of autonomous vehicles. Imagine if a vehicle is supposed to recognize a stop sign, but they incorrectly recognize it as a speed limit and then just go right through the intersection. So you can see this can be a major issue. In the same paper, he brings up the idea of transferability as well. This idea is that if you have, let's say you don't have access to this very expensive, maybe Amazon model or model from Microsoft, but you have access to maybe your own model on your own computer. And the idea of transferability is if you can attack your model, those same samples can then also are effective in attacking this unknown model, what we call a black box attack. And so these are two very important areas of research that are constantly looked at when we look at adversarial examples, and the same is true when we go into the domain of text. All right, so I want to look at some of the now continuous attacks. These were attacks that were first developed in the area of computer vision, and I want to introduce these because a lot of the initial work in text adapts these attacks. So the previous paper that I introduced that first highlighted this existence of adversarial examples in deep neural networks, they used this approach called the box-constrained limited memory Broyden-Fletcher-Goldfarb-Shannon algorithm, or LBFGS. So the algorithm wasn't specifically just for adversarial examples, but it was for the way that the problem was formulated. And it's formulated here where L stands for the loss function and delta is the change that you add to the original image. So the goal here you can see is they're trying to change the image so that it gives a different label here. And we want to minimize that change here, which they use the L2 norm here to measure how much change was given. And so to optimize this kind of constraint problem, a popular algorithm at the time was this LBFGS algorithm. Soon after this paper, because this is relatively intensive in terms of computations, they developed the fast gradient sign method. And so here what they do is they simply look at the loss function's gradient. So if you know in deep neural networks, when you're training, there is this forward passing of the inputs to the output. And then there is a loss function that evaluates how well the machine learning model is doing. And they back propagate the error of the loss function back up to the input level. And they do that by doing gradient descent. And they look at the loss function and they go in the opposite direction of the loss function because you want to decrease the value, the gradient of the loss function. Well, here in the fast gradient sign method, what they do is they want to go in the direction. So that's where they just take the gradient. And of course, with respect to each input here, X, and they just take the sign and add a small epsilon to that. And this is the image that you add on to the original. And this paper is where we get that picture of the panda being classified as a gibbon. Later on, Papernaut also writes an adversarial attack on images classification called the Jacobian saliency map adversary. And here they don't look at the loss function. They look only at the actual function of the model. They do the forward derivative, and they look at how each input influences in terms of the gradient towards each output. And they make a map, which is what they call the saliency map here, of the forward derivative, where we see the values that are important in terms of affecting a grade change in the output. So then they add values to those based on this Jacobian matrix and are able to produce average examples in that way. Later on, another group, Carlini and Wagner, which is where we now coined the C&W attack, they also return back to the formulation that was in the original paper from Sajady. But instead of using the LBFGS, they essentially just use gradient descent to optimize the problem. And in addition to that, they also use other norms. They use the L1 norm in addition to the L2 norm. And they also look at the L infinity norm. And they also look at several different kinds of cost functions. And they show that the C&W attack is effective using all these different kinds of variations. So now I want to talk a little bit about how it's difficult for text. So we were just looking at attacks in the image domain, and what's unique to the image domain is the features, the inputs are all pixel values. They're continuous. They range from 0 to 1 if you normalize, or pixel values between 0 and 255. And so there is, kind of this idea of continuity between values. However, in text, we all know that it is not continuous. It is very much a discrete environment. You either have the word or you don't have a word when you speak in human language. And because of that, we have to kind of address this situation when we start to first use deep neural networks in text, and also if we wanted to perform an adversarial attack on that. I wanted to mention malware detection as well, because they essentially do the same approaches. They are also discrete with respect to the input features being either byte codes or bytes of instruction, or even source code. They convert that in the same way that's used in text, so that it can be then used by deep neural networks to train on. Also perturbations. For images, we just saw the image of the panda that's classified as a gibbon, and there isn't any noticeable difference to the human eye. However, as humans, when we're reading text, especially if we're looking at someone else's paper to kind of edit and review, we quickly catch on to simple typos and grammatical errors. And so these kind of small errors don't really exist in the idea of adversarial examples for text. And so we need to address that as well if we want to study this for text. And then semantics. For the image, we saw, again, going back to that same image, if you can recall, that the change to the human eye is very different visually. You can't really see those changes. And even if you make a lot of changes, it's still easily recognizable as a whole. However, in the human language in text, a single word can completely flip the polarity of a sentence, introducing a negative like not, or changing a word from something like imperceivable to perceivable. These are small changes, but they make a very big difference in semantics. So all of these things we need to kind of consider if you're doing research in text. So I want to briefly now talk about kind of what are the approaches used to apply deep learning as a whole to text, and then we'll look at some papers that attack it. First is the idea of transformation. Because text is discrete in nature, we need to find a way to make it continuous. Early methods just did kind of what we call a bag of words, where there is just a huge vector where the dimension is the size of the vocabulary of any possible word. And it's basically true if that word exists in whatever you're doing as the input. We now have dense embeddings. One of the most popular ones is word2vec, and here we have an example that I pulled from tutorial on word2vec. And essentially, they're able to train in an unsupervised manner the idea of what a king should be numerically as a fixed continuous vector. And here you see on the right kind of images, this kind of highlighting the values. And the words here are king, man, and woman. And this is just a very toy example, but you can see that in this vector, the values are very cold or negative. So maybe it's trying to pick up, it's able to pick up in this dense embedding the idea of a human here. And so Word2Vec is able to do this for a huge vocabulary. And so we often use this for a lot of the way we convert text to an embedding, a dense embedding. And then we can use those representations to then process through any kind of deep neural network that might be used in computer vision or in general, whatever neural network of choice. We also have this idea of more powerful transformer-based models, where they also have an embedding idea, but they are more powerful, and they are more expressive, and they're full language models. And so these two things are kind of the approaches that are used to apply deep learning in text. Now, some of the core architectures are the recurrent neural network, the RNN, and the convolutional neural network, which if you're from the computer vision community, you should be very familiar with that. So in the RNN, essentially you take a neural network and you just keep feeding back itself some special information. So if this is the input here, if you can imagine, it goes into the network, and usually it'll give an output that you can use, but it also, the RNN kind of has this idea of hidden states or hidden kind of encoding that it feeds back to itself, where we kind of call it the context of the current, what we've seen so far, and it feeds it back to itself so that the next time step or the next word or sentence or even character, when it goes through this network, it also takes into account what happened previously. And then you do this several steps so that you consume the whole text, and eventually you have a final state that you can then compute a softmax or whatever you want to do for your classification. For the CNN, this consumes everything at once. So this X is different from this X, because here the X is time step, you know, the first word, the second word, the third one, and so on. And here you have all the words together. They go through some kind of a convolution where the idea is you filter certain words that are linked and you find dependencies. And as a result, they produce kind of a context of the whole thing together. And you can produce that as a single vector. And then this is what is used as the input to then produce an output. We also have to look at the idea of granularity. I kind of briefly touched on it as I was explaining these architectures, but there is the character level, the word level, and now there are systems that consume at the sentence level as well as a part of the processing of the text. And so these are kind of the ideas that will become important when you go into research, not just for adversarial examples, but just text in general for deep learning. So for the remainder of this talk, I'm going to talk about some papers that have arose in adversarial text, which I coined kind of the short for adversarial examples in text. And I will look at it from 3 dimensions. The first is the approach. And here what I want to focus on is the way they produce the attack. Are they just simply adapting from one of those continuous attacks? Or are they using what has become a bit more popular lately, what we call gradient free, where they don't even need access to the gradients of the model and are still able to produce attacks. The second dimension is the attacker's knowledge. Do they have full access to the model when they're doing their attack, or do they have no access to the model when they're doing their attack? So this is the white box and black box setting. And then also I've noticed that in this last dimension, the attacks kind of, because of this idea of we're trying to keep similarity to the human eye, some of the work goes in that the human can still understand the text even though there's a bunch of typos or synonyms that are not as popular. So I use the out of vocabulary, which is often used in text processing, OOV. And so these kind of attacks, I say they use an out of a vocabulary, where essentially they're trying to give words to the model that fool it because it's never seen those words before. And then there are models where they want to use the words that the model is actually familiar with, but still produce the attack. So this is what I call the semantic saving. So we'll look at papers in these kind of 3 dimensions. The first paper I want to look at is Papernaut also wrote a paper. It wasn't specifically for text, but he did do it for recurrent neural networks, and he did it on albeit an artificial data set, but still it was a discrete data set. There was a sequence of 3 numbers, a sequence of numbers going into the RNN, and it's trained to produce a sequence of numbers that match those numbers. It was very artificial, it was random, but that was the goal of the actual task. And then he applies his previous approach, the JSMA, to the RNN. And what he does for this paper is he essentially takes the RNN. As you know, this is the cycle that is feeding back to itself. The X goes in, there's a hidden state, and then the next X goes in, and it's kind of repeating here. So instead of looking at it that way, he kind of unfolds every single time step. And then you have essentially a feed forward of several layers. And he applies this JSMA to this fully unrolled layer, and then he's able to produce an adversarial attack. And here, again, it's not text, but he shows that there is existence and weaknesses in recurrent neural networks, which is important. And it kind of spurs on the idea that there is also probably a good chance that adversarial text does exist. In the next work, they get closer. So in 2017, they get closer to this idea of adversarial text at the text level. So in here, the group of Liang, they adapt the fast gradient sign method. The victim models are character and word-based CNN models. And they also approach with both a white box and a black box attack. And you will see that in text, the black box attack is not such a far, it's not completely the same as what you will see in the vision, although there are some that are adapted from the vision based on the idea of the substitute model. You attack it and you transfer it leveraging transferability. But often you see in the black box attacks for text, they kind of find the words in a different approach. And they do that here and in several papers. So in this paper, what they do is they have two ideas, one called the hot training phrases and the other called the hot sample phrases. For the training phrases, they're looking at the training data and essentially the idea of the good word attack. They're looking at a series of characters or a series of words that come up frequently for the legitimate class or whatever specific class that you see. Then they look at those that are unique to the other class or the target class that you see. And so you have this set of hot training phrases that are quote unquote for good and for bad that are unique. Then they look at the test data. This is the sample that you're trying to perturb, to change, to make it into an adversarial text and fool the victim model. And they essentially look at the text and find areas of the text that are highly influential on the output. And so those what they are coining the hot sample phrases and positions. And then they take a combination of these to finally produce the final output. And here's an example of what they do. So you can see here, this word historic comes from their cycle through algorithm for the hot sample phrases, and they simply delete it. And then here, this is a phrase that they crafted based on hot training phrases, and they inserted it here. And here they do a modification to the word castle, where they replace the L to the 1. And then this completely gets misclassified, although a human reading this would be able to pick up on it easily in terms of still understand the content of this text. In the next paper, they also do an adversarial attack, and it's a little bit different. Here they adapt the JSMA. And what they do here is they use the gradients for the white box attacks to show which words are important. And they also use the same gradients to see which sentences are the most important. So to rank the sentences, what they would do for the input text is they would take each sentence individually, pass it to the victim model's classifier, and it'll give obviously an output with a value, and that'll give the score of that sentence. And then they order the sentences based on these scores to show importance. So if you're trying to go from positive to negative, you want to show the most positive ones first, and then you go descending down to negative. And then they take each sentence in turn in that same order, and they do each word individually. The way they score each word is they just delete that word and give the sentence without the word and compare it to the sentence with the word. And then the difference in those scores are used to evaluate the importance of that word. And so this gives an idea of what are the most important words to attack first in the most important sentences. And for the black box attack, they don't use the gradients, they just query the model. And what they show in their paper is that the black box attack is almost as effective as the white box attack. And here they do use out of vocabulary as a target. So they take these influential words and produce a perturbation on them individually. And so you can see here the original text, and there are 3 words that they change. And here they use a replacement of a single character. Over here, another single character. And over here, they insert a space to break this apart. So you can see easily that they're trying to attack the out of vocabulary-ness of the victim model, because none of these would appear in proper text or this. And essentially, you can see that the model is completely confused, because originally it knows that this is negative sentiment, but now because of these 3 words not being recognized, it's now classified as positive sentiment. And to the human here, perception-wise, they can still understand the gist of the sentence, even though they have these strange errors, typos come up. So now I also want to look at transformer models. So transformer models, the wave of transformer models has been, reined in as one of the best thing that's happened to NLP in terms of language models. And so here, this paper does research into attacking the transformer model. And they essentially do the same thing where they rank the words, rank the sentences, and attack the words by replacement or modifying, but they take a more systematic approach in the way they change. So previously, you can see that they are introducing just kind of typos to address out of vocabulary. But in this approach, they specifically want to use semantic equivalence. They want to avoid just using out of vocabulary. They want to use words that seem proper to the human speaker. And so what they use is not just the same word embeddings, but they also use synonym-aware embeddings. What that means is the embeddings, normally, they just relate words that are close to each other in meaning. So king and queen, male and female, but they're opposites. However, the synonym-aware embeddings keep track of actual synonyms. They also do a part of speech check. And when they want to measure how much the sentence has changed, they use this idea of universal sentence encoder, which research has shown is very good for multi-domain text. And they show here the results of the accuracy. So you can see this is sentiment analysis. It dramatically drops all of these. And even the BERT model, you can see it is affected dramatically by this attack. Now, the last paper I wanted to introduce, and I'm getting short on time here, but just a couple more slides, but is the gradient-free attack. So there are papers now coming out with gradient-free where they don't even care about the original model. And it's not as simple as in the continuous model where you have your own substitute model and you look at those gradients. It's a very gradient-free based attack. So in this attack, they bring in the idea of genetic algorithm or evolutionary algorithms. And so the idea of evolutionary algorithm is you have a population of several possible potential solutions to the problem. And the solutions to this problem in adversarial text is to find an example text that is slightly changed, but keeps its meaning, but still fools the classifier. So that's the problem we're trying to solve in adversarial text. And you have a bunch of solutions. And what they do is they are very careful in enforcing the constraint of keeping semantics true, and at the same time, focusing on the classifier being fooled. And they go through, you have a population of randomly produced solutions using their perturbation, a simple perturbation algorithm. And then they go through a crossover at each generation where they find 2 parents and they mix those answers together. And then they do a mutation, which essentially reapplies that perturbation that was used for the population creation. And they do this for several generations, and over time, just like the survival of fittest idea in evolution, they find the best answers. And here is one of the examples that come from that paper. So you can see semantically, there's no typos. This is pretty natural terms of reading text for a human. And you can see that it changed from negative to positive once again. So they're able to do the problem of adversarial examples and with great effect. And you can see there are no typos, and these are natural human words. All right, so just a brief kind of introduction to the defenses that are using. Obviously, a lot of the original attacks were out of vocabulary focused. And so you can simply just do a spell check or grammar check to then recover the original text for those. And so a lot of the newer attacks avoided that altogether, as we just saw in that most recent paper that I showed. And so the idea that's used often in the continuous domain of adversarial training is also applied for the text domain. And there's also an approach where they do detection strategy where they try to detect if the text was augmented in any way from a natural human writing it, and then they have a strategy to kind of handle it from that perspective. So since I'm now out of time, here's a list of references that I used for the different papers and slides, and now I am open to questions.
All right, so thanks, Daniel. And any questions? I think you can unmute yourself, right?
Yeah, that's right.
Yeah. So any questions?
Hi, let me ask a question.
Mm-hmm.
So you showed a survey on papers that do adversarial attacks on natural language as text, but you could also have machine readable text that is not actually natural language, right? I'm
Right.
sure there are works in that area. Are you familiar with this? Is there a lot of work in that area?
There is some work in that area. I did read a paper of structured text, so structured data, which kind of is not, natural human. It's just kind of maybe like a data sheet, and they kind of produce. There is, I think that's the closest that I can recall. But yes, there is some work growing, not necessarily natural language. Also, there is work in the malware detection, which is not human language, but it's still discrete nature. So there is some overlap in terms of the way the approaches are done for adversarial examples in that discrete field.
Thank you.
Mm-hmm.
Okay, so any other questions? We have a few more minutes. Daniel, can I ask you one question here?
Sure.
So for this field here, and what do you think about the trends? Like, what will be some important problems here, and also for defense side, right? So what will be some important techniques you can actually use?
So personally, my personal opinion, I think there's a lot of promise in the gradient-free area of research for adversarial text, mainly because I feel it's kind of a different flavor than what you will find in adversarial examples in the continuous domain. Because a lot of times, what I've seen so far is they'll do kind of the same attack on a substitute model, and they focus more on that. Although I'm sure there are other more novel techniques in the continuous domain as well, but there seems to be a lot more, it's more approachable in the text domain because it lends itself better to those kind of gradient-free attacks. And I would be interested maybe if there's some benefits to apply those attacks back to the continuous domain as well.
So for the second question that you asked, Ping, about how do you defend against these kind of attacks? Yeah, that's a very, very good question. So, defense, you have to be very, very careful because there was a very interesting paper which showed that obscuring gradients is not the right way to go. So some people said that, oh, because people are using gradients to construct attacks, so let's obscure the gradient, right? And so these authors, what they showed is that 7 out of 8 methods that are based on obscuring gradients, they were able to defeat. And the only method that they were not able to defeat was using ideas from robust optimization, robust statistics, And so that's the only approach that survived against their attacks. And so, if you're going to work in defense, you have to be really very careful because, you kind of have to sit down and anticipate, just like in cybersecurity, right? You have to think about what the attacker can do. Similarly, when you're designing a new defensive method, you have to sit down and anticipate, okay, what kind of attacks can people make on this, and see if you can, survive those. Not just try out the existing attacks, but try to anticipate, some of the attacks of the future, right? So the defensive field is really much harder, and I guess the best thing would be to have an oracle. The authors of those of that paper, maybe you can use them as an oracle or a service. Does my technique work or not, or are you able to defeat my technique or not? That would be nice. But in another approach that you can take is to collaborate with the statistician, right?
Mm-hmm.
Because they know about robust statistics, and optimization theory people know about robust optimization. So I think defensive work has to be collaborative.
All right, thank you. Okay, so so the time is up. So let's thank the speaker again, Daniel. Very good presentation. And we will move on to our first paper presentation. That's from Hao Liu and Boyan Wang. And they are going to present, the title is Mitigating File Injection Attacks with Natural Language Processing.
Right.
So
the first step is to do a recording play, and then they will do a couple of minutes of remarks.
Okay.
Okay, and then we'll do Q&A. So Avisha, can you start the recording?
Yeah, I think it's recording now.
Yeah, okay. So
okay, all right. Okay, so please start.
Avisha, I can't hear the audio, so you may want to make sure that you have the audio setting turned on.
Hello everyone, my name is Hao Liu.
Okay.
Today I'm going to present our paper, Mitigating File Injection Attacks with Natural Language Processing. My advisor is Boyan Wang, and we are from the University of Cincinnati. So first, what we investigate in this paper is about automated text generation with restrictions on the word selection for the file injection attacks against searchable encryption. So what is searchable encryption? Well, the searchable encryption can search over the encrypted data without accessing data or queries in the plain text. So by using the search encryption, the server is able to do the search function based on the those encrypted files and the corresponding metadata. So it only returns the files containing particular keywords that we try to search. So the search encryption can protect our privacy from the malicious server who's spying on your emails and your search queries. However, the search for encryption decays the access pattern. Well, it means the server can learn which encrypted files were retrieved given each query. So for example, if we send a search token CD to the server, and the server returns search results C2, C3, C5, and we also send the search token GHGK to the server, and they return the search results C3, C4. Similarly, the search token is VBDA, and the server returns files C2, C3, and C5. So based on the search result here, we can infer that the search tokens ESCD and VBDA might be a similar keyword because they have the same access pattern, which is the search results. So based on the access pattern, the attacker can infer sensitive information. So here is comes to the file injection attacks. So for the file injection attack, the attacker is trying to inject a set of deliberately crafted files, and the goal is to learn the content of the queries. The assumption here for the attacker is that the attacker knows all the keywords, and it can send inject files to the client, and it can observe the access pattern on the server side. And the assumption for the client side is that once the client receives a file, and it will use search encryption to encrypt it immediately. So how does a file injection attack work? Well, for the file injection attack, it can inject log T inject files for a total number of T keywords, and each file includes T over 2 keywords. For example, if we have 8 keywords in total, we only need 3 files, and each file includes 4 keywords. So for example, the file 1 includes keyword K5, K6, K7, K8, and file 2 include K3, K4, K7, K8, and file 3 include K2, K4, K6, K8. So if we have the search result is 0, 1, 0, so we would infer the keyword immediately, which is K3, because it has the unique search the access pattern. So we examine the attack in the real world by trying to say if the attack is practical. So we assume the client used the search encryption to protect the email privacy, and the attacker performs the attack automatically. The challenge here is that how to generate readable crafted email automatically. And also, each crafted email should include a set of keywords, which is a certain number of words in each set. So here is the test generation problem with a restriction on the word selection. So by solving this problem, we introduce 2 language model methods, which is the first one is n-gram language model, which is based on the Markov assumption. Specifically, the next state is based on the previous state or several states. So for the n-gram language model, the next word prediction is only based on the previous n-1 words. So the input for the n-gram language model is the corpus in the word level. And so the n-gram language model is trying to build the Markov model by learning the probability distribution of the sequence of the words. And it output the word selection. It output predictions based on the word for the word candidates, and then you can select the word from the prediction candidates based on your restrictions. The second model we use here is a non-short-term memory network language model. We treat it as a black box model. Since we have the restrictions on the word selection part, because we have to inject a set of keywords in each file, so we design the customized roles by replacing the keyword the word with the